All right, so we have one more talk by Kisun Lee before the break. Go ahead.
Yeah, thanks. I'm just really happy that I can contribute to this wonderful workshop. And first thing is, compared to the Thomas talk like previously done, this is not really a complete package. This is more like a preliminary implementation of my recent paper. And also, our talk really barely talk about algebra, but I would just talk about some other non-algebraic object, which is such that like algebraic geometers might be interested in. So my aim is I want to talk about the numerical certification and why it is important, especially if you want to do some computational algebraic geometry. So this is based on the joint work with the Tim Duff. And let me just begin. So I just want to briefly review about the homotopy continuation again. So Maggie gave a talk yesterday, and she introduced this homotopy continuation. And this is just solving the system's polynomial system using a homotopy. So what I mean by is that if you have a target system which is given by capital F that you want to solve, and how do we solve this? We consider star system, which is given by capital G, whose solutions are already known. And then what we're gonna do is we just construct the homotopy between these two, and by tracking t equals to 1 to 0 or 0 to 1, depending on your preference, we can find out the all solutions of capital F from the solutions of capital G. This is the idea for homotopy continuation. But for today's talk, I want to talk about how this is gonna be implemented in practice. And also Maggie mentioned about this one. So what we're gonna do is we will just think about, in order to track the solution path here, we will just think about the tangent line of the solution path in order to get the next prediction for the next point on the path. So this step will be called as a predictor step. So what I mean by that, using the tangent line of the solution path, you just guess the next point of the solution path. But if you look at this arrow and the point of this arrow, of course, this is not quite far away from the solution path. So you should refine this, which is called the predictor step. So by using like a Newton's method, you refine them in order to get some point which is close to the solution path. And this is the predictor corrector step. This is like a certified, again, tracking the homotopy is just repeating these two steps like predictor and corrector, predictor and corrector. This type of method is called the predictor corrector method. This is how we usually implemented homotopy tracking. And this is probably the part that I want to mention today. But I just want to show you some demo of how this can be done in Macaulay 2. And I'm sorry that I didn't upgrade my Macaulay 2 yet. But yeah, there's a package Anton implemented, which is called numerical algebraic geometry, that you can use the homotopy continuation. Let me just show you how this is gonna be work. You should start with like defining the polynomial ring. Let me just go with the two variables example. Let's think about this target system capital F. We will just think about this system here, and I want to say that square root of 2, 1 is the one of its solutions, and I want to find out the solution for this, which is the solution for this capital F. And then in order to do this, we will think about the star system, and hopefully all of us here know how to solve this. Like it is plus minus 1, plus minus 1. We know the solutions of this one. Let me just pick one of them. And then there's a function called track. It tracks from G to F from this solution P. So if you find out this solution, then you got this one. Let me just think about this result here. This looks like a square root of 2 and 1, but however, the problem is it is not really square root of 2. It is approximation of square root of 2. So this is the one issue that you should think about when you use the numerical techniques to solve the system's equation, because numerical techniques returns numerical solutions, which means that it is approximation. So in order to use the numerical techniques for some kind of rigorous proof or something like that, then certification is needed. What I mean by that, you should verify that your solution is correct, which is obtained from this type of numerical techniques. So I want to talk about numerical certification here. Of course, there are several ways to define this one, but I just talk about certification in this way. Suppose that you have a system F, and then we will say that X is a numerical solution, and we will say that it is certified if you can find out some small region that contains unique solution to this capital F. If you can find out such a region, then we will say that X is certified. Why we define certified solution in this way? Because if you have this type of small region, then by using, for example, Newton's method, you can refine any point in this small region to get this x star up to arbitrary precision with infinitely many steps or something like that.
So you must have some assumption for that region to do that.
Yeah, right. So you should have some small enough region that you can guarantee the Newton operator converges to the unique solution. Okay. So, but what I want to say is this process will be done after you find out the numerical solutions. So this is something like a posterior certification. This is post-processing. After you find out the solution, you do this type of certification, and then you check that your solution is correct. So I think this is a really nice time to mention one of Frank's paper, and well, thankfully both authors for this paper are here. So but this paper is a really nice paper highlighting the importance of the numerical certification and also providing the robust software, which is called Alpha Certified. So it certified numerical solutions using something called alpha theory. And then, yeah, this is really nice paper. I just read like more than like 100 times throughout when I was a PhD student.
That may be more times than I read it.
Okay, yeah, well, I just read, well, because this is about my dissertation anyway, yeah. But one ironic thing is, even though I mentioned Frank's paper, what I want to say today is it is not enough in some cases. So what I want to say is, post-processing certification is sometimes not enough because it does not verify the correctness of the path tracking. So it checks the correctness of the numerical output computed, but it doesn't check the correctness of the path tracking. So why it is important? Because in some computations, for example, if you want to compute the Galois group using monodromy technique, just like Thomas presented yesterday, then correspondence between the solutions of target system and star system are important. So, and this type of thing cannot be verified from the post-processing certification. That's why we want to talk about certified homotopy tracking. This is what we want to do. But let me just convince you a little bit more why we need certified homotopy tracking by showing two bad scenarios that can happen from the practical homotopy continuation implementation. First one is path jumping. Path jumping is a situation something like this. Suppose that you are sequence of predictor corrector method. You start from the second solution path and it jumps into the first solution path. This is the path jumping. What's wrong when this path jumping happens? Suppose that first solution path tracked correctly, then you got two first solutions found twice. On the other hand, the second solution never found. Okay? So you got false multiple solution, and also you got one low solution in this case. And probably even worse is the path crossing. Path crossing is literally speaking, crossing happens when you track these solutions. What's really important thing is the issue is you lose the correspondence because first solution finds second solution finds first solution. You lose the correspondence between solutions between target solution and star system, target system and star system. And also, as I mentioned, in monodromy computation, we really need to think about the order, again, correspondence between solutions, and it is hard to detect because anyway, you find out two solutions anyway. So this is the two bad scenarios that can happen in actual implementation of homotopy continuation. So certified homotopy tracking guarantees the path tracking, and then you guarantee that there's no path jumping and crossing. And this is what we want to do, and here's some previous works that I want to cite here. So this is the certified homotopy tracking that I want to talk about. But in order to do this, I want to introduce interval arithmetic. So this interval arithmetic, this interval is really closed interval that you learn from the calculus class, like a univariate function defined as a closed interval, something like that. What I want to do is I want to introduce the arithmetic operators between intervals so that you can add interval, multiply interval, subtract, divide intervals. So what I want to do is I want to give arithmetic operators between intervals here. Why we do this? I want to conduct conservative and guaranteed computation using this one. Let me show you some example. Let's say that we have f of x, which is a univariate function. And suppose that it is defined on -2 to 2 interval. then if you evaluate this function over this interval, what I'm gonna do is, in interval arithmetic, you just really plugging in this function. This is not really precise way of speaking, but anyway, I would just plug in this function that you got negative 12 to 12. But this region is actually much larger than actual image, which is negative 4 to 4. So interval arithmetic gives you some region which is probably larger than the actual image, which is obtained in a very conservative way. So kind of the idea of using interval arithmetic is if you prove something for the region obtained by the interval arithmetic, then of course your property should be true for the actual image. This is kind of the idea why we use the interval arithmetic. But using this one, I want to use the Kropotkin method because I want to combine this interval arithmetic with the Newton's method. So we define some interval operator, which is called the Kropotkin operator. So you don't really need to read this carefully, but like this is some interval box that you can make with this input interval. This is obtained by somehow mimicking the Newton operator. So this is really like an interval version of the Newton operator, something like that. And we have the following theorem. If you have this Kropotkin operator, if it is contained inside your original input, then it proves the existence of the solution inside capital I. Furthermore, if you satisfy this further norm condition, then you can also use this for proving the uniqueness. So that, as I mentioned, I want to find out the small region that you can prove the existence of uniqueness so that you can use the Kropotkin test for the certification here. So let me show you.
So is the second condition to this contraction on an operator?
Yeah, it makes the operator to be contraction. And also because this is, it is a kind of interval version of the Newton operator. Once you iterate this, if you make the Kropotkin operator of the Kropotkin operator of the Kropotkin operator, then you can refine the solution as well. Let me show you the example here. So this is the same system, and then let me just give you this input interval. This is the interval that you want to certify, or in other words, this is the interval that you believe that square root of 2, 1 is contained. And then let me check that if it is true. Of course it is true, but anyway. Like, if you compute the Kropotkin operator, you got this interval. And I wish you can check that this Kropotkin operator is contained inside the original input. And you can check the uniqueness condition as well. The Kropotkin test is true. Therefore, your input interval I contains a unique solution of this capital F. How can we find out this? Maybe you can apply this Kropotkin operator many times, then you can refine your solution as well. Okay.
So I mean, this is the case that when the Kropotkin method returns true in the second condition, the Newton's method then will converge.
Oh, when the Kropotkin test succeeds, then Newton method should be convergence guarantee. It is guaranteed.
It might be cheaper to run Newton iterations.
Yeah, right. So like that's actually what we're gonna do here. So we just check the Kropotkin test and then we just refine it by using the Newton's method. All right. But I want to use this Kropotkin method for homotopy tracking. How can we do this? I would think about the parametric version of the Kropotkin test. So what we're gonna do is, I will just slightly modify the slides. I will define Kropotkin operator here. But we have capital T interval, one more parameter interval here, because we want to think about the homotopy. Homotopy is something like a system with the parameter T, so that we have one more variable T here, and then we will think of a time interval, which is contained in 0 to 1. Now we have the following same theorem, which is the parametric version of the Kropotkin theorem. So we can also check the existence and uniqueness using this Kropotkin theorem. This is just quite naturally proved by applying Kropotkin operator, like a Kropotkin test at each time t inside your time interval. So now probably I'm ready to give you some kind of naive idea of the certified homotopy tracking. Let's say that you have this homotopy path between two systems. Here's the input interval that you want to begin with, and then I will think of a time interval, and then they will give you some region interval box here. And then we will apply Kropotkin method here in order to check the uniqueness and existence. If it passed, then we proceed. This is kind of the idea for the certified homotopy tracking. And you can see that there's some adaptive choice of intervals here because their sizes are all different. I will mention this really soon. But what I want to tell you is, of course, this is one prototypical algorithm which is also in the paper, but I want to talk about using tilted box. If you use a two-tip box, which is obtained from some proper approximation of solution path, maybe you can do a little bit more sophisticated tracking. So let me just talk about how we can get this two-tip box here, which is called preconditioning step. Suppose that you have this solution path, and this interval is given. This is the input interval that you want to consider, which is centered at x0. x0 is approximation for some point on the solution path. And then what we're going to do is, I will do the predictor and corrector. You just predictor and corrector, you get x1, which is the approximation of another point of the solution path. Now we connect this x0 and x1 by red line segment. And then we will consider interval box centered at this red line segment. And here's the two-tip box. This is how we get the two-tip box here. This type of way of getting this two-tip box is called preconditioning step. And probably one more remark that I want to consider is, so each step of tracking, you have this two-tip box every step. But what we're going to do is, if you apply interval arithmetic here, it will have some overestimation for some reason. So we apply shearing map in order to make this two-tip box to be rectangular, and you can avoid overestimation. Okay? So this is some kind of minor trick that we used, because if you use this two-tip box directly, then it has really like a overestimation here.
This is because your intervals are actually parallel. Is that right? I mean, your intervals are product of intervals into your coordinates.
So maybe I can say in this way. So your interval two-tip box is linear in t. And then evaluating with the time variable makes a really overestimation of it. That's why we want to have rectangular, which does not depend on t-value. Maybe I can overview the algorithm real quick. So suppose that you have a homotopy. We proved this for parameter homotopy, not linear. Well, in our example, we will use a linear homotopy, but you can do this for parameter homotopy. Suppose that you have a non-singular solution path. And I will think about the input interval here. And from this one, of course, we should think about initial time step, which is given by dt here. And from this one, you can define this time interval. And I will talk about this really soon, scaling constant. I will talk about this really soon. But anyway, we will construct this two-tip box. And then we will apply Kropotkin method here. If the Kropotkin test passed, if the Kropotkin test was successful, then we multiply lambda value in order to increase the radius of the interval and the time step. Because if the Kropotkin test was successful, why don't you attempt with the larger size example? So we just increase our box and then we try with the tracking in order to make the tracking to be faster. Okay? But if it failed, of course, then we decrease by multiplying 1 over lambda, and we try with a smaller interval here. This is a kind of the overview of the algorithm. Now let me show you how this works. Well, as I said, this is a preliminary implementation, and here's the very crucial reason here. So unfortunately, complex interval is not implemented in MECLI 2 yet. So in order to, but real interval is implemented, but complex interval is not yet. So we define complex number field in this way with the additional like a variable I here, RI. This is somehow weird way. And then what we're gonna do is whenever you encounter I square, we evaluate that to be -1. It is super inefficient way, but we just do it because there's no complex interval yet. Hopefully it should be done. But we will define polynomial ring in this way. And then target system and start system, I will define the ring for the homotopy. And here's the homotopy. I just use some gamma value here for the randomization. This is a linear homotopy. Let's choose this dt to be 0.05. I intentionally chose this. And as you know, this is the star solution and moment of truth. There you go. Every time it succeeds, it will show the process something like this. And then the last digit is the number of the iterations. So it terminated in like 57 iterations. This is how it works.
So the 57 steps.
57 steps of the, so there are 57 interval boxes computed.
Yeah, because originally it's 120 yet, so it had failed quite a lot, I guess.
Yeah, so, yeah, right. So actually, like Frank mentioned about this one, so if you change the dt value, it changes the performance as well. Let me just try with the dt, which is 0.4, which is much larger than 0.05. It terminated quite fast. What is the ideal value of dt? We don't know. This is what I want to think about at this moment. It is not studied in our paper yet, but well, there are some initial constant that you begin with. At this moment, you just choose reasonable value and hope for the best. That's what I can say, but I want to think about some more analysis about this one as well. Let me give you some more non-trivial example, like Katsura 3. Yes.
I mean, you start with something rather small, and I guess it never increased very much.
Yeah, like it is.
Whereas here, I guess it shrunk. It's hard to see the alpha beat. It looks like it shrunk at first, and then it got it grew.
Yeah, and then it actually changes a lot. It depending on the system as well. We got those questions, I guess. Yes. Equals 1.
Yeah, why not? It'll fail, but then it'll shrink until it actually makes that.
That's what I think. Like maybe I think I can try with the 0.9 as well. Like there we go. 0.9 is fine. How about 1? I'm very concerned about. Oh, there we go. Well, this is just simple enough, I think. Yeah, let me go with some benchmark example. I just chose Katsura 3. This is this system. It is a polynomial system with 3 variables. This is still quite small, but I just want to use this one because I don't want to take too much time on this. Here's the star system. And then here's the homotopy. Let me choose dt to be 0.3. And then let me go. It will take a while. Then also, I just chose random gamma value, so I don't know how much time it will take. But yeah, it is sometimes entertaining quite watching this. But, oh, there you go. It took about like 13 seconds. So, but as I mentioned, what I want to point out is we use very weird way of complex interval implementation. And whenever we encounter I square, we change that to be -1, which is really inefficient. So we actually don't know what is the time efficiency for this type of algorithm here. So what we do in our paper is we experiment with the real homotopy. We construct some system with the real solution, with the real solution path, so that we don't need to use the complex interval. Then it will show the actual speed of this algorithm here. So we just consider the system which is motivated from low-rank matrix approximation problem. So let me just show you this example. So we have this one. Here's the homotopy. So Katsura 3 was 3x3 system with the with the 3 variables. Now we have 6x6 system, which is slightly larger, twice larger. And this homotopy has real solution path from this solution. Okay, so it's slightly faster, like a real homotopy. I think that this should be some kind of the speed that we want to achieve with the complex interval implementation eventually.
I see you chose this one because the ambient dimension 6 is equal to the ambient real dimension 3 complex.
Well, I think, but that's slightly more than that because like it is, well, how we implement our complex interval is not like increasing the dimension, but yeah, so yeah, I mean, like what's done in the complex interval in our implementation is slightly more than that, so that I think, yeah, it is not quite fair to compare this time and that complex interval time, I guess. Okay, so yeah, this is time result. Probably it is also in the paper if you're interested. So, but I just want to talk about future direction because this is still proof of concept implementation. We want to think about robust implementation. Of course, for Macaulay 2, we need to implement CCI first, complex interval implementation first, and then, or I'm just thinking about implement this in Julia because there are some other like already known interval package there. So I'm thinking about this. This is some question that I mentioned before. What is the ideal choice for DT or initial radius? We don't know yet, but I just want to think about how to get this. Of course, it depends on the system. Sometimes, in our example, large size of DT shows the faster tracking, but it is not always the case. And finally, I didn't mention here, but I just said that whenever you 2-tip box apply shearing map, we just make this in the rectangular interval. But when you do that, you lose the sparsity. Even though you have a nice sparse structure in your system and homotopy, you might lose it by using this shearing map. Then how can we avoid this? So maybe I just want to improve the rectangular origin algorithm without using tilted box. So this is kind of the point that I want to improve when I just implement this, consider this robust implementation here. Maybe I can stop here. Thank you.
Any questions for Kisun?
Thank you. And this first formula you wrote is the convex linear combination. You put the gamma over there between the F and G. What gamma is?
Oh, what is the gamma there? So
Yeah, the first formula you wrote.
What's the gamma track?
yeah, gamma trig is, for example, okay, I should go all the way back. So in our homotopy definition,
The first formula.
there you go.
Yes,
We
yes,
multiply
gamma
this
there.
gamma there.
Yeah.
For example, let me just put it this way. Suppose that your star system, target system are all real. But if you want to track those solutions, but in any way your solution path may go to the complex solutions, but the Newton map is real map, so it tries to stay in the real space. So by applying some complex random number, you just make your homotopy to be complex so that your complex homotopy tracking should be available.
Is there any physics meaning or?
Well, we usually choose some random complex number with the unit magnitude or something like that.
Yeah. What it means is, so instead of going in the complex thing between 1 down to 0, you go along a arc of a circle where the direction is gamma. It's a symmetric circle. This way, in C there'll be finely many points that are where the Jacobian vanishes. So you want to avoid those, and one way to avoid those is take a random circular arc. That's what it's doing.
In some sense, there's
It's fun
some
to work it out, actually.
geometry over there. It's the curvature. Okay, thank you.
Oh, maybe I just want to add one more remark. Eventually, I would like to implement this for certification for Galois or computation or something like that. Eventually, I want that level of implementation eventually.
Any other questions? I have one question. I think there's two different kinds of adaptive precision here, where one has to do with the size of the square that you're starting from, and the other has to do with the time step t, how long the time step is.
I'm sorry, can you?
When you make these rectangular boxes,
Okay.
you have a square that generates the box, and then you have a length of step that you take.
Yeah.
So if you make the box smaller, you're making those smaller together?
Well, it is totally user's choice, but it is better to have ratio is not really too big or too small.
Okay.
So currently we don't know what is the ideal.
But if it fails and a rectangle needs to be made smaller, the two are made smaller together?
They smaller together.
That's my question.
So yeah,
Okay.
ratio does not change.
Okay.
Ratio does not change.
Is the homotopy put into a differential equation before applying a predictor method?
No. So much to be put into it. No, we just no, we don't use actually differential equation, but just like an inverse of Jacobian matrix.
I mean, you're solving the Davydenko equation.
Yeah.
And the predictor method is some off-the-shelf method for approximating.
Yeah, right.
So I think it's implicit.
Yeah.
Any other questions? Let's thank the speaker again.
Thank you.